Welcome to the chapter 9 videos on flowing fluid. So we've already talked about the forces inside of a fluid, which are just the pressure that we're going to consider. Now, pressure is not the same thing as a force, but pushing out in all directions uniformly is the only type of stress that a fluid can support. And we usually refer to that as just pressure. And we found that for still fluids, that pressure increases as you go down in them. It only depends on the density of the material, the gravitational field, and how far you go down to get, and how that relates to how much the pressure increases. And then that in turn implied that there was a buoyant force and there was net pushing up on an object. What we want to see is how does this story change if the water is moving, like in pipes or in your circulatory system. Now, the first thing that we have to do before we can get into the pressure part is describe how do you describe the flow of a fluid. Now, there's two types of ways that you would generally try to do this. One is the way that we talked about it so far, like how many feet does the water move down the pipe every single second, so a speed. But you can also talk about fluid in terms of something called a current. Now, current is going to have a specific technical definition, which we'll get to right now, and it has a specific symbol, which is going to be in capital I. And it's not quite the same meaning that you have in everyday language. When people talk about current in everyday language, they're often actually referring to the speed that the fluid is going. So, for example, if you're talking about a river and people, you mean like the rushing current, where you have a water flowing down through rocks or something like that at a really high speed, and they might think of the Mississippi River, for example, which is very placid, as having a very small current or low current. But that's not what we mean. The roving rapids, the water that's kind of rushing through them, that's a high speed, and the speed of the water in the Mississippi River is very slow. But it's actually flipped. The rapids have a low current, and Mississippi would have a high current. Because here's what we mean by current. Imagine you're sitting along the bank of that river, and you're asking how many gallons of water flow past that point every single second. That is the current. And the current depends on the speed, but also on the cross-sectional area. How big of an area is the water flowing through? The Mississippi River is enormous, and so therefore it ends up having, even if it's going very slow, a very large current. Whereas like a narrow little rapids, it's going to have a much smaller cross-sectional area. Now you can go through and you can find the exact relationship through it using the equation right here. And I'm going to show a derivation of the equation I equals AV, which is the current equals the cross-sectional area times the speed of the water. It's not actually that hard to calculate, you just have to kind of visualize it. So where this comes from is imagining watching water flow past a point like right here. And you let it flow for some small amount of time. Well, the water is going to move down the pipe from here, in the case I've drawn it, over to the right. So the amount of water that's actually passed through that spot is delta V, the thing that's in dark blue. If you want to calculate how much that volume is, you can notice that it's a cylinder. And if you take the volume of a cylinder, which is the cross-sectional area, times the height, which in this case is the cross-sectional area times how far the water moved in that time period, I'm going to call that delta x. Then when you plug that back in, I'm adding the geometry to the original equation, well, you get a cross-sectional area, but then you get delta x over delta t, which is the speed of the water. Note, it doesn't have to be like a circular cross-section for this to work. In fact, just so long as the cross-sectional area doesn't change, this formula will work. And even if it just doesn't change rapidly enough, which technically this only works over really infinitesimally small time periods, in which case the water goes an infinitesimal distance, and so the area can't really change in that short distance, then this formula will work. Now, one of the reasons why current is really useful to talk about is because you can compare the current at different points along a single pipe or vein or something that carries water pretty straightforwardly. And here's the idea. If you know that water is emptying into some region at, say, 5 gallons every single second, it better be coming out at gallons at every single second, or it's going to be the volume of water in the middle is going to be increasing or decreasing. So, for example, if you put it in 5 gallons per second, and you're pulling out 4 gallons per second, then the volume inside is increasing at a gallon per second. Now, that can happen if there's like a bucket that you're filling up or something, but we'll specifically be looking at cases that are called steady state flow. Now, the condition of steady state flow means that the current and the pressures at any given point remain constant. Not that nothing's moving, but if you just ask, how many gallons are going past, through this pipe right here every single second, that doesn't change. So it's basically like you can run water through the pipes, but say, for example, you've turned on the sink, but you don't like change the sink. So it's flowing at the same rate. And then the water flowing through the pipes is the same over time. And if you have this case either where you're having a buildup or a drain out, like you put in 4 gallons but pull out 5 gallons every single second, then you're draining the water on the inside at a gallon per second. Then you have you have an unsustainable process. You can't drain out water out of a pipe forever. You can't put more water into a pipe, increasing forever. You're going to either run out of room or you're going to run out of water, depending on which way you're going. So if it's staying steady, the current staying steady, then you can't be in either case. You have to have the same amount of current going in as out because the volume at any area can't be changing. So this is sort of just another way of saying that you can't just like get rid of water. And then if the water is really incompressible, the amount of water is given by its volume. Because normally just like its mass, like how many kilograms of water are we talking about? And if it was compressible, you could shove that into a smaller area. But if it's incompressible, the volume can't change for a given amount of water. And then when you add in, then that as a concept would mean that the current flowing into any area equals the current flowing out of any area. And if you have a very like one entrance point, one exit point in your pipe, it becomes simply the area, cross-sectional area on the side that's coming in at times that speed is equal to the cross-sectional area that's coming out at times its speed. If you had like one way in and 2 ways out, then the current going in would equal to the sum of those 2 currents flowing out. And the equation would look a little bit more complicated. But same basic idea. Now this is useful because if you're just looking along pipes, you can see how the cross-sectional area changes pretty easily. Just is the diameter of the pipe getting bigger or smaller? And then that tells you whether the speed is increasing or decreasing. And then it tells you something about the kinetic energy, which is where we're going to go, about energy considerations. So let's think about water flowing through a pipe. And we're going to have a case where you're going to have some frictional loss. You're going to have some rubbing on here. Physically, the way that it actually comes is that you have like water rubbing against itself. It's warming itself up, and it takes its mechanical energy and it pushes it into gravitational. It pushes into internal energy, warming it up. I realize I have the wrong symbol here for college physics. I should write this as PEG for the potential energy. 1 second, I'm going to fix it. Apologize for that. Okay. So if you're taking energy out of mechanical energy and you're putting it into internal energy, just friction does, where's the energy coming from? Because if you have like a horizontal pipe, the height of the water isn't changing as it flows along, so there's no gravitational potential energy changing. Normally, it would come from this kinetic energy. If you slide something horizontally across the ground, it slows down, right? But in this case, if the pipe has a uniform diameter, so the cross-sectional area is the same, well then it has the same current on both sides and area, so it has the same speed too. So therefore, it's not gaining or losing kinetic energy either. It's not any real springs in this case. So where would the mechanical energy be coming from? It turns out that the answer is pressure. Now, we haven't talked about pressure has anything directly related to energy. We've talked about it as a force applied over an area. Well, here's the idea. The way in which pressure relates to energy is that if you say, imagine that you had a syringe and you stuck it into your pipe and you shoved a small volume of water into that spot. You added water there. Well, the pressure in a fluid is pushing in on the water you're adding in, and it has to be shoved out of the way. So the water that's being injected in must press outward on the surrounding water, and as it goes into a region of higher pressure, it would lose energy. It's going to do work on the surrounding environment. And if you want to go through and actually calculate how many joules it takes to do work to push the water, the surrounding fluid. I use water as an example, but there's many fluids, including gases. But in general, if you want to push the fluid out of the way, it depends on the amount of volume that you put in, and it turns out it's proportional to the volume that you put in. So there's a fixed rate of how many joules of work you have to put into the fluid to shove it into a region of higher pressure per milliliter. And it turns out that the number of joules per cubic meter literally is the pressure in pascals. So you can think about this as a force per area, or you can think about it as an energy density. So the amount of energy per volume. In this case, it talks about the amount of energy you would have to lose in order to go into a region of higher pressure to kind of shove it out of the way. So what's going on here is that as you lose energy to warming up the environment with friction, instead of coming from a kinetic energy or potential energy, it's coming from a loss in pressure. So the pressure will drop as it goes through the pipe. Now, we'll first talk about the case with no frictional effects, so it's easier, and then we'll get into fluid flow with resistance, which will include that friction. The way that you try to figure out how the pressure changes throughout a flowing pipe that has no resistance is something called Bernoulli's equation. And this is really just an energy conservation equation. Now, it's a little bit different because what we're going to talk about is not the change in the energy, but the change in the energy density. So not how many joules does a particular amount of water gain or lose, but instead how many joules every single milliliter of water flowing down the pipe gains or loses. Now, if we consider with the case of energy conservation, where we have no loss in energy from the surrounding environment, then we just look at the changes in each type of energy density. Pressure is one type of energy density. Gravitational potential energy is another one. And kinetic energy is our third one. If you plug in the formulas for changes in gravitational potential energy, mg delta y, and changes in kinetic energy, 1/2 m delta v squared, then you just have to modify them a little bit. Because if you're asking as an energy density, then you're going to divide by the volume of that fluid. And when you do that, if you take a mass and divide it by the volume, that changes the mass into a density. So it's rho g delta y instead of mg delta y. 1/2 rho delta v squared, not 1/2 m delta v squared. So that's conceptually where this comes from. The big idea is that you can tell what's going on with some of these terms very straightforwardly by just looking at the pipe that it flows through. If the pipe goes up, that means gravitational potential energy increases, or if it goes down, it decreases. So just seeing the height change in the pipe tells you about the change in gravitational potential energy. Seeing a change in the cross-sectional area tells you about how the speed is going on. So rather than looking at the speed, because you can't really know that by just looking at a pipe, look at this diameter. As the diameter decreases with a constant current, so here, if the diameter is decreasing, the A out is smaller than A in, and then correspondingly, V out is bigger than V in. So it must be speeding up as if it's through a smaller area to have the same amount of water flow through. So two of those terms, you can just basically look at the pipe or arteries, whatever it has flowing fluid through it, and then figure out what's going on. And then the pressure you can't directly see, but you can calculate it from Bernoulli's equation. So I want to give some example situations, not necessarily like things you're going to calculate, but how we understand a few common scenarios. So one thing, if you haven't heard of it, there's something called an aneurysm. An aneurysm is a case where you have a blood vessel, and I will attempt to draw a blood vessel as sort of a simple cylinder. But it enlarges. So it has like a bigger area inside of it. There's like a bulge in it. Now, there is a change in pressure you get just if the fluid flows up versus down. But that's kind of normal. That's just how it works. What we want to see is what happens due to the pressure of the presence of the aneurysm. How does that affect things? So we'll set this vessel horizontally so that we don't care about gravitational stuff. We just care about changes in pressure due to the area changing. Because here's the thing you want to think about. If you talk about the pressure on the inside of the aneurysm, then you're talking about this area. And if you're talking about the area normally in the blood vessel, like the pressure you normally have in the blood vessel, then that's where you have the normal cross-sectional area. Now, if I have fluid flowing through this case, which through in that direction, that would be, in this case, the fluid would be blood, then my cross-sectional area in would be smaller than my cross-sectional area out. Not meaning out of the whole thing, but at the second point that I'm considering, which is inside of the aneurysm. Now, I don't lose any blood between those 2 points, so I know that then the current in is equal to the current out of those 2 points. And so therefore the area in times the speed in means the area is equal to the area out times the speed that's coming out at. So since the area is larger inside in the aneurysm, then the speed must be slower. It slows down as it opens into a wider area. But let's think about what's going on with Bernoulli's equation. So I have the change in pressure, the change in gravitational potential energy, density, and the change in kinetic energy density here, or like this. If the height's the same between these 2 points, here and there, then there's no change in gravitational potential energy. If it's slowing down, then this number is going to be a negative number. The final velocity squared minus the initial velocity squared is going to be less than 1. Now, some number plus a negative number equaling to 0 means that the first number must actually be positive in this case. So that means the change in pressure is positive. In other words, that the pressure increases. And the pressure increases as the area, even more as the area gets even larger. So now you have an unstable situation. The reason why you develop an aneurysm is that there's a weakness in the blood vessel, and that pushing outwards bulges it out. That then increases the pressure even more, which is going to try to bulge it out even farther. And that process will continue until the material, the lining, the kind of walls of the blood vessel, just can't take that much stretching anymore, and it breaks. It bursts. And this is one of the reasons why blood aneurysms are so dangerous, because they naturally involve a weak spot that is pushed on harder and harder the more it gives. And so if you have an aneurysm, you're very prone for that bursting and then having internal blood loss, which can have serious health consequences, including death. And this is why. Now let's take another situation that's not so morbid, and let's take the case of a faucet. If you've ever watched a faucet, you've probably noticed that up here at the top, the cross-sectional area is bigger than down here at the bottom. Why is that? Well, let's talk about that. So what we have, something looks kind of like this. I can draw this, okay? As the water flows downwards, I have the cross-sectional area at the top. I'll call that the area in, and a cross-sectional area at the bottom. Now, the fact that the area decreases would indicate that the speed increases, because we're not losing any water as it flows downward. It's not like some of the water is being diverted off to some side. Why is that? Well, if I look at Bernoulli's equation, there's a few things I can directly tell. One thing that I can tell is the height is decreasing. So the second term is a negative number. The second thing that I can tell is that the pressure is the same at the top and the bottom. How do I know that? Well, I know it's touching the air directly. Whenever you have two fluids, like air and water, connected, the pressure is the same on both sides of the boundary. So if it's 1 atmosphere, for example, up here in the air, and it's 1 atmosphere down here in the air, it's also in the water at both those points 1 atmosphere. So the change in pressure in the fluid is 0 in that case. And this leaves us with just this last term, which means that you have to have a positive number so that it balances out to 0. Now, that means that the kinetic energy is increasing, which means that it's speeding up. And if it's speeding up, and the current is the same, the cross-sectional area must be decreasing. In fact, you could figure out what the cross-sectional area is at some later point if you knew the current. which is basically, how turned on the faucet is, and the area at one point at the top, you could go through, use Bernoulli's equation to solve for the speed at the bottom, and then plug it back into this equation over here and solve for the cross-sectional area, and you could see at any given distance how how much the area decreases by at any given height. So you can like plot this out on software or something.